Dear learners, I welcome you once again in this MOOC session of Principle of Electrical Sciences. I am Dr. Anwar S. Siddiqui, Professor in Electrical Engineering, Jamia Islamia, New Delhi. So dear learner, in previous session we have already discussed the construction of synchronous generator, types of synchronous generator, difference between salient pole and cylindrical rotor generator, operating principle of synchronous generator, generated voltage of synchronous generator and its equivalent circuit. In the current session we are going to discuss the phasor diagram, parallel operation of synchronous generator, operating principle of synchronous motor, and why synchronous motor is not self-starting, that also we are going to discuss. Starting method of synchronous motor, application of synchronous motor. So let us see some components in the synchronous generator. As you can observe in this diagram, we have shown the AVR. AVR stands for automatic voltage regulator. We have shown the fan, we have shown the flywheel connected plate, then we have shown the stator on which we are going to put the armature winding, and then rotor is also visible there in which you will put the field winding. And as we now know that rotor is going to receive the DC supply, so we require the rectifier. It is shown there, it is inside the machine. In both the generator and motor, you will receive the DC supply into the field winding to produce the required rotating magnetic field. And then you have the terminal outgoing lines. The electrical power will go into the machine when it is working as a motor, and the electrical power go out of the machine when it is working as the generator. Now these are the phasor diagram and equivalent circuit of the machine. As you can see that the flow of current in the equivalent circuit is from the induced EMF from E1 to E2. Okay, so obviously we all know that the current flows from the leading side to the lagging side. So in this, E1 is leading the E2. Z is the series impedance and associated phasor angle is theta Z. R is the armature resistance, X is the armature reactance. E1 in this case, when the current is flowing from E1 towards the E2, we'll call E1 as the source and E2 is the load. Power is flowing from the source towards the load. Now, if you observe in this phasor diagram, we have taken E2 as the reference. Okay, receiving end voltage we have taken as the reference. And the current, the series current is lagging this voltage by some angle. You can observe there. So there will be some voltage drop in the resistance, and that voltage is in phase with the current. We have marked this as I into R. So from the tip of this phasor E2, you have IR. And from the tip of this IR, voltage drop in resistance, we have another phasor IX, which is the voltage drop taking place in the series reactance. So if we combine these two vectors, IR and IX, will obtain IZ. In this triangle, we have marked theta Z as well, the series impedance angle, and another angle alpha Z, which is the phasor difference between IX and IZ. So the tip of this IZ, if you join at the starting point of phasor E1, then starting point of this phasor AB will obtain E1. And as you can see, E1 is leading receiving end voltage E2 by an angle of delta. Okay. And in the other section of the phasor, we have marked E2 over Z. This is the current if there is only E2 available in this circuit. And E1 over Z is the current which would flow if you are having only E1 there. But since we are having both E1 and E2 in the circuit, therefore the resultant current is I. So series current, it will remain same in the circuit. This is the three-phase equivalent circuit. We have marked here all the three phases A1, A2, A3, and if you have a balanced system, the phase difference between these three phasors will be 120 degree. So you have the synchronous reactance and armature resistance in each phase. In A1, we have the synchronous reactance, we have the armature resistance there, and we have marked the current as IA1. Terminal voltage is V1, V51. Okay. Similarly, in phase 2, you are having EA2, and we have shown the synchronous reactance, the armature resistance, current is marked as IA2, and you have the V52, the terminal voltage in phase 2. Then the similar equivalent circuit we have for phase 3 as well. EA3, you have the synchronous reactance, you have the armature resistance, the current is marked as IA3. So this is the stator side. You have the three phases there. Okay. Either you will supply the three-phase electricity when you are using the machine as a generator, or you will receive the three-phase supply when you are using the machine as a motor. But in both type of operation, there will be DC supply into the rotor, and you can see in the rotor circuit we have shown the VF. VF is the field voltage. It is DC, which is going into the field winding, which is put on the rotor. So you have the field resistance marked as RF, and you have the field inductance marked as L suffix F. IF is the field current, and by varying this field current through the resistance connected there, we can modify the excitation of the machine. If the current is increased, the excitation will increase, and if the current will decrease, the excitation will decrease. Conditions for putting the two generators in parallel. It is known as the parallel operation of synchronous generator. So we put the generators in parallel to take more load. If the load is going to be more than the rating of one generator, we are going to put another generator in parallel. But before putting the second generator in parallel to the first generator, there are certain conditions which you have to follow. And these are the listed conditions. The phase sequence of the incoming machine voltage and the bus bar voltage should be identical. So either you are connecting the machine in parallel to the bus bar. Bus bar may be a combination of many other generators which are already connected in parallel. Second condition is the RMS line voltage of the bus bar or already running machine and the incoming machine should be same. Okay, so incoming machine should have the this RMS line voltage same as the already running machine or the bus bar to which you are connecting it. The phase angle of the two systems should be equal. The frequency of the two terminal voltages, that is the incoming voltage and the bus bar, should be nearly same. Large power transient will occur when frequencies are not equal. So here in this diagram we have shown two generators which are connected in parallel and together they are supplying the load. Let us assume that generator 1 is already running and it is the generator 2 which we are going to put in parallel with the first generator. So generator 2 is being parallel with the running power system, or let us say generator 1. These two machines are about to synchronize for supplying power to a load, common load. The generator 2 is about to be put in parallel with the generator 1 with the help of this switch S1. This switch S1 should never be closed without satisfying already listed conditions. Now, why are we putting these alternators or synchronous generators in parallel? let us see the advantage of parallel operation of alternators. When there is maintenance or an inspection, one machine can be taken out from the service and the other alternators can keep up for the continuity of supply. So when you are having many machines supplying the load, you can take out one machine for maintenance or inspection and you can continue with the remaining machines. Load supply can be increased by putting more machines in parallel. During light load, more than one alternator can be shut down. So basically, when you are having different machines in parallel, you can go on increasing by putting more machine in parallel, or you can reduce the power generated by taking out some of the machines. It gives high efficiency. The operating cost is reduced. Ensure the protection of supply and enables cost-effective generation. When you have many generators connected in parallel and you have been asked to generate a certain amount of power, you can divide this power among the generators in such a way that the fuel cost is minimum or the your profit is maximum. So this gives you the better economy as well. That's why we have written as the generation cost is reduced. Instead of having a big single machine producing all the power, it is better to have multiple machines put in parallel. Breaking down of a generator does not cause any interruption in the supply. So this will be the major advantage when you are having many machines connected in parallel. Even if you have taken out some machines because of some fault there or because of maintenance or repairing purpose, then the supply continue. So the reliability of the whole power system increases. We all know what do we mean by the reliability. Reliability is the continuous supply of the power to the consumers. So reliability of multiple machines connected in parallel is always better than a single machine, single larger machine. Now let us see the detail about the synchronous motor. When you are using the machine as a motor, I have told you already, in case of synchronous motor, we are taking the alternating supply AC into the machine and or the electrical power is put into the machine and we take out the mechanical power. The rotor is connected to some load and it rotates that load. So through that it supplies the mechanical power to the load. So a synchronous motor is the one which in which the input is the electricity and output is the mechanical power. If three-phase supply is given to armature, a rotating magnetic field is produced. The speed of this rotating field is synchronous speed. You have connected it to the AC and AC has got its frequency, that is F. So the speed of the rotating magnetic field is going to be Ns. Ns is equal to 120 F over P. P, as we already know, is the number of poles in the machine. The stator produces a two-pole field which is rotating in clockwise direction. If field winding is excited, poles are created on rotor as shown in the diagram. You have the north pole and south pole there. The angle between stator and rotor field axis is this angle delta and we call it the torque angle. Torque is, as we all know, is equal to power divided by omega. Omega is the angular frequency. T omega is equal to P. So torque is proportional to sine delta, where delta is torque angle. The torque varies sinusoidally with time. It reverses during each half cycle. So as you can observe in this diagram, during the positive half cycle, you will have positive torque. Torque we have taken on the y-axis, whereas this angle delta is on the x-axis. So during positive half cycle, you have positive torque, and during negative half cycle, you have the negative torque. So equal positive and equal negative torque in a single cycle. As a result, the motor will try to rotate in one direction during positive cycle, and it will try to rotate in the opposite direction during the negative half cycle. But since the moment of inertia of this synchronous motor or synchronous rotor is quite high, so it fails to rotate, in fact. Okay, it will remain stationary. That's why we say that this synchronous motor is not self-starting. And as written there, hence synchronous motor on its own has no net starting torque. Why this synchronous motor is not self-starting? The south pole of stator attracts the north pole of rotor. Thereby it produces clockwise torque in half of the cycle. This rotor rotates anti-clockwise in one instant, and after 10 milliseconds, that is the duration for half a cycle, it rotates clockwise direction. Now due to inertia, the rotor does not rotate in one particular direction and remains stand still, and it fails to rotate. That's why we say that the net starting torque on rotor is 0. Hence the synchronous motor is not self-starting. We have to put some other means to start it. Operating principle. When a three-phase supply is given to the stator winding, a synchronously rotating magnetic field is produced. A three-phase supply given to a three-phase winding will produce a rotating magnetic field. Similarly, a two-phase supply given to a two-phase winding will also produce a rotating magnetic field. But a single-phase supply given to a single-phase winding will not give you a rotating magnetic field. Anyway, in our machine we are having three-phase winding and we are giving the three-phase supply, so we are going to get a rotating magnetic field. The speed of this rotation will be linked with the frequency of the supply. Okay. We already know Ns is equal to 120 F over P. P is the number of poles. Now rotates the rotor with same speed or nearly same speed as synchronous speed in the same direction with the help of some prime mover. Since the rotor by itself is not going to rotate, what we are going to do, we will put some means, and through which we in the starting time will rotate the rotor in the same direction as the direction of the rotating magnetic field with synchronous speed, or with a speed which is very close to synchronous speed. After this, there is a magnetic locking between the stator and rotor moves with the synchronous speed. So now even if you remove that machine, that prime mover, the rotor continue to rotate. So we need to start the rotor initially and then it will continue to rotate. Because the north pole of rotor locked with the south pole of stator, and hence rotor will now experience a net torque and it will continue to rotate in the same direction in which we have rotated it initially. So if you you cut off the prime mover, then this rotor will continue to rotate in the same direction as the synchronous speed, as the synchronous rotating magnetic field. So how this starting push is given to the rotor? There are many means through which we can do it. There are several alternatives to rotate the rotor at a speed almost equal to that of the synchronous speed, and these are some of the methods which we have listed here. First one is using pony motors. You have some auxiliary motors through which you will rotate the rotor initially. Or using damper winding. In that case, this machine will start as the induction machine. Okay. Or as a slip ring induction motor, using a small DC machine coupled to it. So this DC machine will act as a motor for rotating the rotor of the synchronous machine. Applications of synchronous motor. Synchronous motors are normally used for large size loads because in small sizes they are costlier as compared with induction machines. So if you compare the synchronous motor with induction motor, one major difference is that in case of synchronous motor, we are going to have constant speed. These machines will rotate either at synchronous speed or they will not rotate at all. So speed control is not possible in case of synchronous motors. They will have constant speed. These are constant speed machines. Whereas in case of induction machines or in case of DC machines, we can control the speed. The major advantage of using synchronous machine are as follows. The power factor of synchronous machine can be controlled very easily by controlling the field current. Now this is a major use of the synchronous motor. An overexcited synchronous motor acts as a capacitor, as a condenser. So we all know that the condenser or capacitor, they are the source of reactive power. So an overexcited synchronous motor supply the reactive power to the system. Whereas an underexcited synchronous motor acts as an inductor. It absorbs the reactive power. So by exchanging this reactive power with the system, you can control the power factor with the help of a synchronous motor. And this improvement in power factor is carried out by varying the excitation. Excitation variation I have already explained to you. When you vary the field current, through that we are changing the excitation of the machine. So if the induced EMF is more than the terminal voltage, you have the overexcitation. And if the induced EMF is less than the terminal voltage, you have the underexcitation. It has very high operating efficiency but constant speed, remember. For operating speed less than about 500 RPM revolutions per minute, and for high power requirements above 600 kilowatt, synchronous motor is cheaper than induction motor. So for those applications, we can always look for the synchronous motor. In view of these advantages, synchronous motors are preferred for driving the loads requiring high power at low speed, such as reciprocating pumps and compressor, crushers, rolling mills, pulp grinders, etc. So with this, we finish off this second session of our synchronous machine. Thank you very much.